Okay, so let's start. It's my real great pleasure to introduce Martin Ziegler, who is a professor from KAIST, the Korean Institute of Advanced Science and Technologies, Advanced in Science and Technology. So this is one of the top institutions in South Korea. He is a leading expert in particular computability aspects. And so I think we are all very excited to have him here. He is with us for 1 month, so he's a visitor at our chair. And I think this talk should also serve as, giving everybody a bit of introduction in what he's interested in and what he's working on. And so in that sense, Martin, the floor is yours. I think we are all very much looking forward to your presentation.
Thank you. Thank you very much. Yes, and I'm extremely grateful for this opportunity. So my Korean university has this new program where selected foreign faculty on a competitive basis are allowed to spend the time without lectures at their home country. So this is a trial. Usually this is not possible for other faculty and not for Korean faculty. So I'm trying hard to make it worthwhile and work out so that this will be continued in the future. And I'm extremely gratitude to Gitta for enabling this stay here. I've been very warm received by all of you. I've had great discussion with many of you guys, and actually I've known Gitta for a long time, or a long time ago in Bavarian, and I'm extremely impressed, I have to say, about the kind of research that is going on here. This is very broad research, and the thing is, if there's a chair for functional analysis, then the group members will, of course, do more research in functional analysis and give presentations on functional analysis. But the proverb, the saying, if your only tool is a hammer, then every problem will look like a nail. So if there's a chair on functional analysis, then any problem will look like a problem in functional analysis. And that's kind of natural. But what I experience here in this group is an entirely different approach, right? Here it's a problem-based approach. Problem is this new technology, this new endeavor of artificial intelligence. And the tools to approach this problem in this group are so diverse. I have never seen such a broad kind of techniques to approach this problem from all possible sides. And this is I'm very impressed by it. Yeah. So that being said, yes, let me start by sharing my screen. So can you see this? Hide the meeting controls. Right. So here are two terms. First term is a lesser sin, right? So that's a term from theology. A lesser sin theologically is something where you have to suffer in hell only for a finite amount of time, not infinite amount of time for the graver sin. But the other term is Verjährung. I think there's a corresponding English translation, but this is a legal term. This is something kind of like expiring when you have done something wrong legally. Eventually it will expire, either if it goes unnoticed or if you have suffered proper punishment, then afterwards you're considered Verjährung. So why do I mention this? Because since I came here, everybody says I am known from computability theory. but this is one of the lesser sin. This is verjährt. I did do computability theory when I was in Paderborn, but I have moved on a long time ago. So I want to ask for your forgiveness and use this opportunity to advertise what I have been doing since I stopped basically working on computability theory. And that is, I'm working on computer science for continuous data, of which computability theory is indeed a part of, but only one brick in this big picture. And here's a web page that kind of gives you a general impression, but this talk here should also serve as a survey of this direction of research. Computer science for continuous data, as opposed to traditional computer science for discrete data, and as opposed to computer science for discretized data. Discretized data meaning take continuous data and chop it up into small pieces so that it fits into the traditional realm of discrete data. You know, there's this anecdote, you know, plywood. So you take a perfectly stable tree like an oak and you cut it into small pieces. That's discretization. And then you process the small pieces and then you glue them back together to form a table or a chair or whatever. This is a kind of a anecdotal way of looking at discretization in computer science. And to be fair, I still discretize data, but I want to hide it from you, like a table made of plywood hides that it is made of plywood. Instead, there's all this, yeah, it's hidden, basically. So that's a kind of joke to begin with. And let me start with a paradigm that I personally have been following. And the paradigm is, yeah, so starting, there's a problem, first investigate its computability. If the problem is not computable, then we need to workarounds. But if it is computable, then we can look more closely and ask, what is its computational complexity? That only makes sense to even ask once it has been established as computable. Once we know its complexity, and hopefully it is of a good complexity, like something polynomial or even more specific, cubic, quadratic, linear, then it makes sense to start having a student implement it, right? I wouldn't want to ask a student to implement an exponential time problem because that only leads to frustration. So this is a three-stage process, and this is traditional in computer science. What I'm doing is the same for the continuous case, the non-discretized data. Okay. And computability for continuous data, this is what I did basically up to my habilitation thesis. And since then, so now this is expired. And since then, I've been looking at complexity of continuous problems. And for the past 8 years in Korea, also, I had my students start implementing algorithms that process non-discretized data. So, and when it comes to processing continuous data, there are basically two major models of computation that serve both as guide and also as framework to devise and analyze algorithms. One is the Blum-Shub-Smale model, and the other is the model of, so I'm going to call it analytic machines. Blum-Shub-Smale model is an algebraic model where one only has algebraic operations. So whenever something transcendental arises, then the Blum-Shub-Smale model is already at its limitation. The Blum-Shub-Smale model has been used very successfully to extend P versus NP problem to other realms beyond the discrete setting, and it is still considered as a major a framework for proving P different from NP. So that's so-called geometric complexity. But when it comes to implementing things, it has some serious deficiencies. On the other hand, analytic machines, that's what Alan Turing actually introduced in his 1936 paper. And here are some other people who have been working on analytic machine as a model for processing continuous data. And these two models are incomparable. So for example, they agree that arithmetic operations are computable, but the sign function is computable in the Blum-Smale model, but not in analytic machines. On the other hand, exponential function is computable by analytic machines, but not in the Blum-Smale model because, yeah, it's a transcendental function after all. So both have their advantages and disadvantages, and one major goal of mine has been to kind of bridge the gap between these two models, because in practice, what people in numerics do, when they write programs, they think in terms of the Blum-Smale model, they think as if they operate on real numbers exactly. On the other hand, analytic machines, being Turing machines, are very inconvenient and haven't really made it so far into numerical practice. So what the one major result group is synthesis of both model, changing the semantics of the Blum-Smale model a little bit so that it now becomes equivalent to analytic machines, but much more convenient to write programs in than using analytic machines, Turing machines. So, but as of course, any model of computation is an idealization and becomes unrealistic in some sense or another. For example, if you have a digital computer, your PC at home, most people would say this is an instance of a Turing machine, but actually, strictly speaking, it's an instance of a finite automaton because it has finite memory after all. Only the memory is so large that in many ways it behaves as if it has infinite memory like a Turing machine, but of course, infinite memory like a Turing machine cannot be realized. So both idealizations have their merits and their limitations as idealizations of digital computers, and the same applies to Blum-Smale model, and the same applies to analytic machines. So with this disclaimer, let's move on to a short history of computing. And what I'm trying to say here is that historically, science became before engineering. So science, in the sense of being the foundational discipline, and engineering being the applied, the implementing discipline. And as I already mentioned, this paper by Turing from 1936, where we introduced a Turing machine and defined for the first time a model of computation for digital computers that preceded the actual realization of a digital computer by 5 years, namely Konrad Zuse's Z3 computer became operational 5 years after Alan Turing had introduced this purely mathematical model. During that time, in 1936, the computers that Turing was using to break, for example, the cryptographic code of German military, this was not a universal computer. It was specifically made for a particular task, but not a universal. SUSE Z3 is universal, and SUSE, of course, was aware of Turing's work and arguably used that partially as guidance towards building his Z3 computer. Another example later in the 70s, Xerox PARC developed a computer with graphical user interface, mouse, Ethernet, and multitasking, demonstrated it's a proof of concept. Here you see it, but it never became commercially and widely accepted because it was ahead of its time, but it served as guidance to Steve Jobs, who visited Xerox PARC, bought the patents, and then first built the Apple Lisa and then the commercially successful Apple Macintosh computer, which everybody could afford. Computer with graphical user interface, mouse, Ethernet, multitasking, 14 years later. And since then, basically every computer has a graphical user interface, mouse, Ethernet. So this was ahead of the time. And third example is Peter Shor's quantum algorithm, the algorithm for factoring integers on a quantum computer. No, that's not true at all, because at that time, there was no notion of a quantum computer. All these notions were developed later, and then people started trying to build these computers, physicists and engineers, and this is still in progress, as you know, right? So 53 qubits, I think, is current world record. But all this started and is going only because Peter Shor first demonstrated that it would have an immense practical advantage, and then engineers starting to theoretically, and then engineers started to try to implement it. So this is kind of the direction that I favor, from theory as guidance towards engineers. So let's look at some other examples. So when you have a large-scale software project, software endeavor, right? Something that involves many people, large group, then this can use all the technology, all the methods developed by traditional computer science by first specifying the problem, then investigating its computability, then its complexity, then thinking about the programming language to use, what is the semantics of the programming language, how is the formal verification possible for that particular programming language, and only subdivide the problem into abstract data types, and only then start implementing. I mean, for a small project, we can skip some or maybe even all of these stages. But as the complexity grows, software complexity, gradually all these stages become more and more important. For the discrete setting, this is kind of a state of the art. For continuous data types, the situation is not as advanced yet. When we talk about real numbers, real function operators, we have the definitions for specification, we have the computability theory. I did that until 2008. Complexity theory, and what is currently in development, and something I will talk and research is about programming language semantics and formal verification for programming languages that process real numbers and real functions and real operators exactly, and abstract data types over real numbers. And when we move even further away to other continuous data types, such as analytic functions or continuously differentiable functions or Sobolev function, then even the definition of complexity is currently still open. So for example, what is a polynomial time computable L2 function? That is a question that has been bothering me a lot, and I haven't not yet been able to come up with a good definition for a polynomial time computable L2 function. Computability theory for L2 functions has been developed over the past few decades, but complexity, that's where we're currently stuck, and that's what I have been working on. And definitions, yeah, definitions are even lacking in this realm. Good definitions that reflect practice, but also that have nice closure properties, structural properties. And here's a quote by Dorrit Seilberger: "A good lemma is worth 1,000 theorems." And I'd like to modify that. Right, Seilberger is at Rutgers University. I'd like to modify that and say a good definition in turn is worth 1,000 lemmas. And we're even missing the definitions when talking about continuous structures. So here's a brief overview of my talk. I'm not intending on covering all the topics. Time is short. So I want to talk about the power of abstraction first. So what you see here is a first transistor ever. Okay, so the first transistor is a semiconductor. Its operation is heavily based on quantum mechanics. So, and billions, literally billions of these are in your desktop computer. Now, who of you knows quantum mechanics? Who of you has knowledge on the semiconductor theory, electron wave bands? Could you raise your virtual hands if you know quantum mechanics? Okay, some of you do. Okay, great, great. Now the point is, people don't need to know quantum mechanics in order to use computers. And why is that? Yeah, because all these levels of abstractions that are built on top of that, right? So this is a transistor in a case. And this is a symbol of a transistor, and now you don't need to know quantum mechanics. You only need to know the logical table of this transistor, and then combining transistors into a large number of transistors. More abstractly, this such a Boolean circuit. And now you only need to know the truth table of that Boolean circuit. Putting that circuit into an integrated chip, combining these onto a computer board, comparing that even further into a central processing unit. And now you can forget even what are the basic functional blocks of the CPU, and just can start programming in assembly code. So that's a hardware code. Then there's a basic input-output operating system. On top of that, our device drivers operating system. Then there's a library that supports, for example, fast integer multiplication. And then there's high-level programming language. So many layers of abstraction, and each layer allows us to forget and to ignore the lower layers. That, I want to argue, is a major what allowed the progress of digital computers. Nowadays, everybody can use digital computers. For example, my smartphone here, right? Everybody has a smartphone, but doesn't need to know about quantum mechanics in order to use the smartphone. And another advantage is replaceability, right? So if you have a desktop computer or laptop computer, that's entirely different computer hardware, but the operating system doesn't even need to know about the hardware details because of the BIOS between them. Also, if you have one operating system or another operating system or a third one on the higher level, doesn't need to know, and you can replace the lower levels without affecting the higher level, or put differently, you can use or work in the higher level and make all kinds of different sources on the lower level will be able to run your program in a higher level programming language. So that's about the power of abstraction. And where's difference between hardware and mathematical data type illustrates that importance of this abstraction. Now, some of you might remember the computer game Civilization. Well, it was a big hit when I was a teenager. And at that time, yeah, just to give you a brief background, in this system, it's one of the first artificial intelligence games where the human player chooses one country and rules one country, and all neighbor countries were guided by leaders that were actually a computer player with a limited, very rudimentary artificial intelligence. For example, India is governed by Gandhi, and Gandhi is described with a parameter such, for example, his aggression level is very low, 1. Other countries have leaders with higher aggression levels. Another rule in this game is that during the course, when a country adopts democracy, the aggression level decreases by 2. Now, what happens if you play this game and India develops democracy? 1 minus 2 equals, okay, any guesses? 1 minus 2 equals, mathematicians? Yeah, the thing is, when this game was developed, it used bytes, right? Both for performance and for memory saving reasons. It was developed in assembly code and some basic C, ordinary C. So in a byte, 1 minus 2 is equal to 255. So when India developed democracy during playing this game, suddenly Gandhi becomes very aggressive and will wage war against his neighbor countries, which became a running gap of that game, right? So technically, this is a bug of the game. It's a funny bug, but it's a bug because the underlying data type, hardware data type byte, differs from the mathematical data type integer that we have all grown up with since elementary school, right? So there's a discrepancy between hardware and math data type. Programmers think in mathematical data type, they think 1 minus 2 equals 1 minus 1. But the hardware data type has this wraparound error. And this is basically the source of a programming bug. Now, nowadays, these programming bugs can be prevented because nowadays programming languages have data types that coincide with the mathematical data type integer. For example, in Java, there's the big integer. This is simulated in software using bytes, so bytes still occur, but using a variable number of bytes, just sufficiently number of bytes so that there is no wraparound, so that from the perspective of the user program, it appears if the big integer data type is equal to the mathematical data type of integers. Of course, there's a efficiency lost, but this is compensated by having no or less programming bugs because now the data type coincides with the mathematical data type. Technically, using a variable number of bytes additively hidden from the user. So that's again an example of abstraction, a new layer of abstraction, so that the user program can operate on big integers as if they are mathematical integers. Now let's look at the real numbers. What is the counterpart in hardware? In hardware, it's usually floating point numbers, but we all know that floating point numbers differ from real numbers. They have all these rounding errors and error propagation. That's numerics 101, right? But there are libraries, C++ libraries that overload the classical operations and thus implement data type real number that actually coincides with the mathematical data type real number. So hardware floats differ from mathematical real numbers, but this data type coincides with real numbers. And this again reduces complexity for writing correct numerical code. There's a disadvantage, it's slower, but the slowdown will decrease over time. That's something we're working on and accelerating it to make it competitive. Technically, again, this proceeds by using floats and under the hood, still hardware floats, but a variable number of precision floats in various ways, adaptively, so that from the user perspective, it appears as if they are actual infinite precision real numbers. That's how it works technically. And then building on that data type, one has exact data types for matrices, for polynomials. I can just write 1 over A for the inverse of a matrix, and the library will make sure that all the calculations are performed in sufficiently high precision so that from the user perspective, it appears as if it's really the inverse of a matrix. And these are finitely many real numbers, then there are infinitely many real number data types like sequence spaces or analytic functions with their power series expansion. So this is this can be done, and this is what we're doing. And this, I believe, will become mainstream once we have solved this slowdown. It's a constant factor of slowdown, right? So from a perspective of a computer scientist, constant factors don't really matter. So eventually the benefits will overweigh similarly to the big integer, which nowadays are prevalent. But when civilization computer game was developed, they were not used at that time. So the point here is again, the power of abstraction, adding a new layer of abstraction, software simulating mathematical data types on top of hardware data types, information hiding to increase convenience and to reduce the source of errors. Now this has some consequences, I have to admit. So for example, in numerics 101, don't test for equality, right? When talking about real numbers or floating point numbers. But what can you then do with floating point numbers? If you can test for inequality, then it's a simple exercise that as a Boolean combination of inequalities, one can recover equality, contradiction. So if you cannot test for equality, then also there's no test for inequality and there's no test at all. That doesn't make sense, right? But there's a solution to that. So there's also a theoretical result that says that inequalities are in a certain sense, with real numbers are in a certain sense equivalent to the halting problem. So that's not really a matter of representation, how to represent these numbers, but it's an intrinsic problem. They cannot be compared if they are equal. If they're non-equal, then this is semi-decidable, and similarly for greater or equal. And this leads to, in programming language theory, to the modified semantics of greater comparison, namely greater can now return true if the first number is greater than the second, false if the first number is smaller than the second, and if they're both equal, then it doesn't return at all. That's the halting problem, right? If they're equal, then comparison in these new, in these libraries with the underlying approximation of arbitrary precision, it will not return at all. However, we can have lazy evaluation. Lazy evaluation means it does return, but it returns a new logical constant called u or unknown, but you cannot evaluate that. So that's why it's called lazy evaluation. And this is also well known in logic. Namely, this is called the Kleene Booleans. So Kleene Booleans, false, true, and unknown. And here you see the truth table. For example, true or unknown is true. And false and unknown is false. And here you see the other tables. So if you make a logical formula that involves these extended Booleans, then sometimes the unknown gets cancelled, and you still get a well-defined result, even if there's unknown. And that extends to programming over this two data types, the real numbers, exact real numbers, and the Kleene logic. Let me give you an example. Let's say you have a traditional comparison. I want to compare whether R is greater than minus epsilon for some fixed epsilon. Then the traditional if-then statement is not well defined if R happens to be equal to minus epsilon, because equality, then you cannot, you can make this assignment, that's lazy evaluation, but when you then later evaluate it to execute the if statement, then it will not return. So that gives the challenge to the programmer to write total program using the consumption rule of this Kleene logic. And here's an example how to do that. You make two comparisons, R greater than epsilon and R smaller than plus epsilon, and you see there now there's an overlap, right? When R is somewhere between minus epsilon and plus epsilon, then both will be true. And then use the new choose operation that will execute the first clause, then clause, if A is true. It will execute the else clause if B is true. And if both are true, A and B, then non-deterministically, one of the two clauses will be executed, and it's the responsibility of the programmer for the correct program to make sure that the program still works in this case if both are true. And it's also the responsibility of the programmer that always at least one of them is true. If both of them are unknown, then the program is not well defined. This is kind of like dividing by zero, right? Now, in traditional programming language, when you divide by zero, the program will throw an exception. Here, if you write incorrect code, then the program will simply freeze at this instruction. So it's a new challenge. And from my experience, when I teach this to my students, it takes something between 3 and 6 months for them to adapt to this, because they already know traditional imperative programming. Let me give you another more involved example of this use of this partial comparison, right? So that's the way around this paradoxon, right? Now we cannot express equality as a Boolean combination of inequalities, because now the inequalities is partial, it's undefined, it's unknown when there's an equality. So we cannot express equality here. Instead, programmers have to write code, total programs using this instruction. Here's a more involved example. So here we have a partial semantics of tests. So that's a programming language theorist speaking here. And here we have this choose operation here generalized from the binary case with 2 arguments to the d-array case with 3 arguments. And now we can re-express what has been known in rigorous numerics for a long time as fuzzy test or a soft test. And more generally, programs now operate on 3 structures. The first are the integers. We need integers for counters and for precision parameter. Real numbers, the exact real numbers, but with this partial comparison. And okay, here's a animation. Don't worry about the circles, it makes sense in a minute. And the point is we have a mapping, that's a logician speaking, from integers to real numbers. not embedding the integers as by the identity, but instead embedding the integers from p integer to 2 to the p of real numbers, so that high precision corresponds to very negative integers. Okay, so for example, if you want 10 bits of precision, that means p is equal to -10, corresponding to error parameter 2 to the -10 2 to the p. And I will give you 3 reasons why this is better than the natural embedding p, the identity embedding, or which also occurs commonly in numerics, p maps to 1 over p. 3 reasons. But let me first illustrate here how to write programs with this new formal programming language, theoretical semantics. So here you see again the choose operator with 2 Boolean arguments to make sure that at least one of them is always true in the fuzzy test. And here's a more involved example, namely trisection. You know, bisection for looking for a root of a given function f. But if the middle point of the interval happens to be the root, then that's an equality. And then bisecting for left or right will not be possible because testing for equality doesn't work. You need to make sure as programmer that there's always an overlap and always at least one of them is true. And the workaround is to extend bisection to trisection. Okay, so here's the code. Now you see also the circles here. Again, with this choose operation, and the trick here is now to divide the interval not in 2 parts, but into 3 parts, and to check the sign on the 2/3 and on 1/3 simultaneously using this choose operation. And if the underlying function is promised to be non-decreasing, then it's will guarantee that at least one and possibly both of the conditions will hold. And therefore, the problem of bisection does not occur here. The rate of convergence is now a little bit smaller, not 2 to the n number of iterations, but not 2 to the n, but 3 over 2 to the n is the rate of convergence. Anyway, so this is how you write code for processing real numbers with this modified, but now computable semantics, partial semantics of real comparison, which arises from the underlying implementation using arbitrary but finite precision approximation, so that it appears as if it is exact, but the user has to adapt to this new semantics. This is a new semantics I've been suggesting for the modifying for reconciling the Blum-Shub-Smale model and analytic machines. You may also notice a subtle point here. In integers, I've only allowed for addition and not multiplication. Well, to be honest, our programming language, of course, also supports multiplication of integers, but this is logician speaking. Namely, when it comes to formal verification, then we know that formal verification is in general undecidable. This is well known due to Gödel, right? And also Steve Cook wrote a paper about that, because any logical formula about integers in general will have the Matyasevich effect of being undecidable. However, this is known as Pressburger arithmetic. If you prohibit multiplication, if you only have integer addition, then this Pressburger arithmetic is decidable. And so every statement, logical statement, can be decided. And so that gives the justification for formal verification. Now everything that can be stated about such a program over integers without multiplication can be decided, is logically decidable, either true or false. And the famous result of Lou van den Dries, a logician, says this can be extended to two-sorted structure, integers without multiplication and real numbers. but only with a real number predicate like this. And from that, we could conclude that any statement about programs in this structure, the programs that our language can be expressed, is also decidable. So computing over these two structures is Turing complete for real functions. It's as expressive as analytic machines, but much more convenient without Turing machines. It's modifying the Blumenschutz-Smale semantics so that it now has power equal to the power of analytic machines, but more convenient. And also, this two-sorted structure has a decidable first-order theory, logically speaking, decidable, right? Follows from Lou van den Drie's 86 result, a non-trivial consequence. And thus, it allows for formal verification. Any statement about such a program can be decided formally. This is also a model complete. This is a logical technical term. And all this becomes wrong if you replace the error bound 2 to the p or 2 to the minus n with the error bound 1 over n, which is also common in numerics. But if you have 1 over n, then all these nice properties just go away. So structurally, the theory is simply nicer, to be honest. Maybe less practical, but much nicer. Yeah. Anyway, so formal verification. And now, yeah, time is running out. Let me recap what I've said and what is currently going on and what we're planning to do in future. So state of the art of classical discrete computer science, the state of the art of computer science for real numbers, and state of the art of computer science for other general continuous data types, such as, and that's our goal, to head for LP spaces, L2 spaces, and Sobolev spaces. Then I talked about particular continuous data types, namely the real numbers. Of course, we still need integers for counters. If you don't use multiplication, then everything even becomes logically decidable. But of course, you will still write programs using multiplication, or you simulate multiplication by repeated addition. And there's this new logical data type, the Kleene Booleans, with this new element true, false, and unknown, following as a result of a lazy evaluation. So yeah, lazy evaluation, you all know from programming languages, right? So, and then the Boolean connecting Kleene Booleans, and then writing programs, still writing total programs, but using these Kleene Booleans with this new operation called choose, which is a non-deterministic operation, but the user has to make sure that at least one of the two arguments to the choose function must be true. That leads us to the imperative programming language for analytic machines, but using imperative programming as in Blumenschutz-Smale. So reconciling the best of the two worlds. You don't need to write code Turing machines. You write code like in Blumenschutz-Smale programs, but you still need to make sure about this partial comparison. Then, yeah, formal verification. Now the OR logic becomes decidable for this new programming language, since we dropped the integer multiplication. Then what I didn't get to talk about is coding theory, right? So you all know the famous classical coding theory started by Claude Shannon. But this is about discrete spaces, right? The coding theory of discrete spaces. Here we, in order to aim for Banach spaces and yeah, Sobolev spaces, we're developing, we're working towards coding theory of general compact metric spaces. This turns out to be the right setting over infinite sequence of bits rather than finite sequences of bits as Claude Shannon did. And also random sampling, randomized algorithm are very important. Okay, to be fair, that's because I studied in Paderborn, right? Cannot avoid randomized algorithm. But how about random sampling of continuous data? Right? So you can, for example, regularly sample a real number between 0 or 1. But famous open question is if you can also sample Markov chain. So that's Proud in motion. Yes, Proud in motion. There's some technical challenges, and it's not known whether you can really rigorously, in this sense, sample Brownian motion. That's one, right? That's what one of the famous paper from Einstein explaining Brownian. Anyway, yeah. So to wrap things up, yes, recap of what I talked about. Currently progress and in future developing more continuous data types. The current continuous data types can be found here on GitHub. This is what my students implemented. And also there's a YouTube channel teaching about computer science and computer science for continuous data. There are like, I think four entire lectures of 30 hours each are recorded here. So yeah, please subscribe to my channel and like. And yeah, that's all I wanted to say. And there's some time left for discussion. So thank you very much for your attention, and thank you so much for hosting me.
Yeah, thank you so much. I mean, Martin, for an amazing talk. And I think we are all very glad to have you here. And yeah, I mean, I didn't say it before, but yeah, we know each other for a long time now. I mean, since Paderborn, I think I was a PhD student and you as well. So it's great to have you here now. And with this, I open the discussion round.